Welcome to the edge of the cosmos and the forefront of astronomical discovery. Today, we're diving deep into one of the most groundbreaking findings in recent history. With the help of the James Webb Space Telescope, astrophysicist Neil deGrasse Tyson has shed light on an astounding theory. The Webb Telescope has observed black holes from a previous universe that could have played a crucial role in creating our own universe. Strap in as we unravel the mysteries of the cosmos and explore how these findings challenge our understanding of space, and JWST are casting doubts on this established narrative. Neil deGrasse Tyson highlighted that the JWST has detected black holes from a preceding universe, suggesting our cosmic understanding may need a major overhaul. As we delve into the enigmatic findings of the JWST, which baffle astronomers and contradict long-held beliefs, it raises the question, could our theories about the Big Bang be flawed, or might there have been errors in data collection? Join us in this exploration of JWST's discoveries that defy explanation, questioning the accuracy of the Big Bang theory. One of the pivotal revelations involves the detection of incredibly ancient galaxies, challenging centuries of scientific consensus on the hot Big Bang theory, which posits that our universe originated from a hotter, denser, and more uniform state. Proposed as a compelling alternative to conventional theories explaining the universe's expansion, this theory received remarkable validation in the 1960s through the discovery of what is now known as the cosmic microwave background. For over 5 decades, the Big Bang theory has been the leading explanation for our cosmic origins, suggesting an initial rapid expansion or inflation that set the stage for everything that followed. Yet, both the concept of cosmic inflation and the Big Bang itself have encountered ongoing scrutiny from the astronomical and astrophysical communities. The James Webb Space Telescope, JWST, has introduced a new challenge to this narrative. By uncovering early galaxies that are significantly more massive than previously thought, the JWST has added a layer of complexity to our understanding of the cosmos. This revelation of large-mass galaxies in the nascent universe hints at a need to revisit and possibly revise our cosmic framework, as these findings do not fit neatly within established astronomical models. Although the James Webb Space Telescope has been operational for under 2 years, it has already offered unprecedented views of the universe's state a few hundred million years post-Big Bang, challenging existing paradigms and suggesting it's time to rethink our cosmic assumptions. Suddenly, it seems we might need to rewrite the textbooks on the universe's inception. A significant breakthrough has been the rapid formation of vast star-filled galaxies, revealed through the JWST's infrared capabilities. Astronomers have identified 6 massive galaxies from the universe's early days, whose sheer size, if confirmed, could dramatically alter our understanding of how galaxies come into being. Published in the journal Nature, these revelations are based on observations made by the James Webb Space Telescope, offering a glimpse into the universe at 13.5 billion years ago, just 3% into its current lifespan. The puzzle lies in how these galaxies, formed just 500 to 700 million years after the universe's birth, could exhibit a degree of development akin to our 13-billion-year-old Milky Way. These cosmic bodies have a stellar mass that is several billion times that of our Sun, with one giant potentially reaching up to 100 billion times the Sun's mass. For context, the Milky Way contains a star mass of about 6 billion suns. This means that these early galaxies were more massive than our own Milky Way. Astrophysicist Erica Nelson from the University of Colorado Boulder, a co-author of the study, shared her wonder at these findings. Expressing amazement, experts find it perplexing that such massive cosmic bodies could form so rapidly, contradicting previous expectations. The standard model did not predict the swift emergence of galaxies with stellar masses comparable to the Milky Ways in the universe's infancy. This groundbreaking discovery calls into question the traditional cosmological theories, which propose that galaxies originated from smaller assemblies of stars and dust, gradually expanding over millennia. According to this view, matter in the early universe came together slowly. Yet, this account fails to account for the recently discovered gigantic galaxies. Lead researcher, who is puzzled by the rapid development of these colossal galaxies, highlights that this finding overturns long-held scientific assumptions, challenging the belief that the universe's giant galaxies required a much longer period to form. These galaxies have been playfully termed universe breakers, aptly reflecting their role in challenging and potentially transforming our grasp of cosmic evolution. Astrophysicist Emma Chapman, from the University of Nottingham in England and not involved in the study, points out that should these discoveries endure further scrutiny, they could significantly alter our understanding of the universe's early stages. Our understanding of the cosmos might be on the cusp of a dramatic transformation. The discovery of enormous galaxies near the time of the Big Bang challenges the previously accepted period of cosmic darkness, suggesting that star formation could have commenced far earlier than previously believed. Yet, a word of caution is advised by the scientists involved in this research. It remains possible that some of these observed phenomena could actually be supermassive black holes, with what seems to be starlight potentially being the glow of gas and dust as it falls into their gravitational clutches. An astronomer not associated with the research emphasizes that the complexities surrounding black hole formation and growth in these formative epochs are still not fully understood. She interprets the findings not as a contradiction of existing cosmological theories, but as a prompt to delve deeper into the unknown physics that governed the early universe's development. To further substantiate their findings, scientists might turn to spectroscopy, capturing spectrum images of these galaxies to reveal more about their ages. Galaxies from the universe's dawn show a significant redshift, indicative of their light stretching significantly over its journey to us. The greater the redshift, the further back in time we are looking, offering a direct glimpse into the universe's youth. The higher the redshift value, the more the light has been stretched, indicating a galaxy is both farther away and older. Spectroscopy could determine if these galaxies, identified as high redshift candidates, are truly as ancient as they seem, or if they're actually closer, younger galaxies that only appear ancient. In this context, Michael Bond, an astronomer, underscores the necessity for additional observations to verify these discoveries. Nonetheless, he points out that the sheer mass identified suggests an astonishing insight. The total mass of stars in this early cosmic era could be up to 100 times larger than previously believed. Michael Bacon from the University of Texas at Austin offers a unique viewpoint, sharing his thoughts in Nature Astronomy. He discusses the standard cosmological model known as lambda cold dark matter, lambda CDM, where CDE MES stands for cold dark matter. This model describes a universe where ordinary matter and dark matter were evenly distributed in the beginning. As dark matter halos collapsed, they facilitated the formation of the universe's first galaxies, with some of the intermingled ordinary matter forming new stars. Bacon notes that there is compelling evidence supporting the distribution of matter in the early universe, gleaned from cosmic microwave background observations. He set out to calculate the amount of ordinary matter that would need to transform into stars to account for the massive galaxies observed by the JWST. His findings suggest an almost complete utilization of available atoms for star formation, a scenario Bacon considers highly unlikely, given that the efficiency of star formation in the contemporary universe is around 10%. Mark Vogelsberger from MIT, who was not involved in the study, commends the paper for its sound theoretical analysis and robust calculations, which he notes are based on minimal assumptions. Despite Bacon's skepticism, he does not entirely reject the lambda cold dark matter, lambda CDM model. He acknowledges that no alternative theory currently offers a better explanation, making the idea of discarding lambda CDM for another model premature. However, the quest for alternative explanations remains open. In a separate but equally intriguing development, Haley Williams, leading a team at the University of Minnesota, announced the discovery of a remarkable early galaxy observed just 500 million years after the Big Bang, also utilizing the JWST. This galaxy's subtle glow adds another layer of mystery to our understanding of the early universe. The discovery by Williams is significantly enhanced through the use of gravitational lensing, which magnifies the galaxy's light. Williams points out that this galaxy's star formation rate is exponentially higher than that of galaxies from a marginally later period, despite its smaller mass compared to the galaxies examined by Bacon. She suggests that this rapid star formation could also apply to more massive galaxies at similar redshifts. Nonetheless, Bacon exercises caution due to the galaxy's compact size, spanning just 105 light-years across, which is considerably smaller than typical galaxies, raising the possibility that it might actually be a globular cluster. To address inconsistencies within cosmological models, one proposition involves tweaking the lambda cold dark matter lambda CDM model to incorporate concepts of early dark energy EDE. EDE models suggest altering the characteristics of dark energy shortly after the Big Bang, potentially resolving conflicts surrounding the Hubble constant and aligning with additional observations. These models imply the necessity for more matter in the early universe. Bacon estimates that in such a framework, the density of matter in early galaxies methods. Another potential explanation involves the possibility that astronomers might be mistakenly attributing some of the observed light to stars, whereas Bacon leans towards believing that this light could actually be emanating from accretion disks around supermassive black holes, considering it a highly likely scenario. Given that only a few of these galaxies have been observed so far, and they occupy a minuscule fraction of the sky, astronomers caution that these findings might not accurately represent the entire cosmos. Joel Leah from Penn State, not associated with the research, proposes that comprehensive statistical surveys could potentially resolve the existing discrepancies. A critical question remains: are these objects truly distant galaxies? Peter Berui from the University of Arizona, also not involved in Bacon's study, raises the point that nearby, low-mass galaxies could appear similar to distant, massive ones. The key to definitive answers lies in further measurements, particularly spectroscopic data, which could determine the actual distances of these galaxies and clarify their nature. Michael Bacon, in anticipation of new data, suggests that within a few years, or possibly sooner, the critical nature of these cosmic puzzles will be clearer. As we await this data, astronomers are exploring various theories to explain these enigmatic findings. One hypothesis posits the existence of an unknown mechanism at play in the early universe, which could account for the appearance of massive galaxies in telescope surveys. The theory suggests that if massive black holes existed early on, they could explain these observations. However, the challenge lies in elucidating how such a significant number of black holes could have formed so early in cosmic history. This inquiry leads to a controversial theory proposed by a Nobel Prize laureate. The prevailing theory of cosmic origins posits that around 14 billion years ago, everything that exists or will exist was contained within an infinitely dense point, or singularity, which then exploded in what is commonly simplified as the Big Bang. This model, however, leaves many physicists pondering how 13.7 billion years could suffice for the formation of the complex structures observed in the universe. A physicist from the University of Oxford is challenging the traditional Big Bang model, seeking to support his theory with evidence from the cosmic microwave background radiation, which dates back to when the universe was only 300,000 years old. This scientist suggests that the Big Bang was not the beginning, but rather one of many events in a cyclic series of Big Bangs expected in the future. Penrose's Nobel Prize was awarded for his work in developing mathematical techniques that expanded upon Albert Einstein's general theory of relativity, as well as his research into the nature of black holes, demonstrating how these dense objects under gravitational collapse to form singularities, points of infinite mass. Embracing his award, Penrose described his theory as unconventional, even calling it crazy, suggesting an ever-cycling universe. The universe will continue to expand until all matter decays, leading to a new Big Bang and the creation of a new universe. In an interview, Penrose shared his belief that the Big Bang was not the initial event. Something preceded it, and that precursor is yet to come in our future. To support his theory, known as conformal cyclic cosmology, which challenges the conventional Big Bang narrative, Sir Roger Penrose points to the discovery of 6 warm spots in the sky, termed Hawking points. These points are each about 8 times the size of the Moon's diameter and are named in honor of the late Professor Stephen Hawking, who theorized that black holes emit radiation and eventually evaporate. The existence of these points suggests the presence of black holes, although detecting them within our current universe, aged 13.77 billion years, is highly unlikely. In essence, Penrose argues that our universe is just one in a sequence, neither the first nor the last, emerging from a densely packed, highly ordered mass that evolved into the complex cosmos we observe today. The existing Big Bang model, which is based on the concept of inflation, does not account for the low entropy, highly ordered state at the universe's inception, unless the groundwork was laid well before the Big Bang itself. According to Penrose's theory, our universe has previously transitioned, and will do so again, into a state of low entropy as it expands towards an ultimate state of emptiness, transforming into a cold, dark, and featureless expanse. Penrose posits that remnants of dead black holes from previous universes or eons could provide evidence for this process, potentially validating Stephen Hawking's hypothesis on black hole radiation. Penrose's 2020 research, published in the monthly notices of the Royal Astronomical Society, showcased the discovery of unusual circular spots in the cosmic microwave background that exhibit higher temperatures. These findings were based on data from the Planck 70J satellite and were corroborated through around 10,000 simulations. In 2018, Penrose pointed out radiation hotspots in the cosmic microwave background as possible signs of evaporating black holes. A 2010 study by Penrose and Vahey-Gurzadyan introduced the concept of cyclic cosmology, suggesting that uniform temperature rings observed in the CMB could be the result of gravitational waves from black holes colliding in a previous universe. As black holes emit radiation and dissolve matter, they play a role in decreasing entropy. As the universe nears the end of its expansion, the remaining black holes are expected to evaporate, further contributing to the transition towards a low entropy state. This process culminates in a state akin to the Big Bang, where space-time geometry transitions from its current jagged appearance to a smoother form. In Penrose's framework, a new eon emerges when the universe ceases its expansion, collapsing into a highly ordered structure and igniting the next Big Bang. Contrary to the prevailing belief that the cosmic microwave background CMB temperature fluctuations are random, Penrose, alongside his colleague Glorian, identified more than 12 concentric circles in data from NASA's double UMAP satellite. These circles are interpreted as signs of gravitational waves from previous eons, lending support to Penrose's conformal cyclic cosmology theory. Although Penrose's hypothesis faces skepticism, its verification would profoundly alter the cosmological field's current paradigms. Critics point out the theoretical challenge of transitioning from an infinitely large universe in one eon to an exceedingly small one in the next, which would necessitate particles to diminish in mass over time. What are your thoughts on Penrose's theory? Do you see it as a viable explanation for our universe's origins, or merely another Big Bang alternative, likely to fade into obscurity? Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and as sessions with experts. Your membership will grant you the chance to participate in live Q and A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.